So we're moving on to magnetism with electric currents. Okay, so today we're going to look at last lesson we looked at how to draw 3D fields on a 2D page. How are they going to indicate to you in your exam that there's a field coming into or out of the page? Okay, they can go left and right and they can draw up and down. How are they going to do in going into and out of the page? Because we're going to need to visualize in 3D. Okay, and they do that usually using dots and crosses. Okay, where the dots signifies the arrowhead, and the tail, the cross symbolizes the tail. Okay, so today we're going to look at how electric current moving through, well, it can be a charge moving or it can be through a wire. Any form of electric current seems to form some sort of magnetic field around it. Okay, so we're going to have a look at this, and then we're going to have a look at how this might affect us if we take a few coils of wire and put them together, or and some other consequences of this. Okay, all right. So it turns out that Hans Oersted predicted in 1813 that a connection would be found between electricity and magnetism. So in 1819, what he did was he placed a compass, which is a magnetic object, near a current-carrying wire, and he observed that the needle was deflected. So the only thing that can deflect a north-south needle is a magnetic field. So he deduced that this current-carrying wire must have caused that, must have a magnetic field of its own. Okay, so he showed that a current-carrying wire produces a magnetic field. Okay, so the next question you might ask is, all right, sir, well, what type of magnetic field? Does it go left to right? Does it go circular? Does it go across the page? How does that work? Okay, we'll talk about that. Now, another interesting thing to note is current is the flow of charges. Okay, so current is the flow of charge. So really, what's causing this magnetism? Okay, what's causing this magnetism? It must be the flow of charged particles. So therefore, you can say that also, if you can basically, narrow it down and say, okay, we know a current-carrying wire produces magnetism. So the thing that must be producing the magnetism must be the charges inside moving. Okay, so then the next thing would come. It would say that we found out that actually moving charges cause magnetic fields. Okay, it's not got anything to do with the wire in itself. Okay, if the wire didn't have a current going through it, there wouldn't be a magnetic field. So it's the moving charges that cause a magnetic field. Okay, magnetic field. Okay, so that's a really, really important thing that you want to note down in your notebook. Okay, that moving charges cause a magnetic field, and because moving charges flow in a wire, obviously they flow all in the same direction, so they're going to unify and form a bigger field. Okay, but a moving charge by itself, if I have an electron, okay, and I shoot it towards this way, it will produce a magnetic field around it. Okay, and we're going to have a look at how that works for current-carrying wires or for charges flowing through a wire, which is the same thing. Okay, current-carrying wire. All right. So let's have a look at this. So it turns out that there's a way of finding out how a current-carrying wire produces a magnetic field. Now you can do this yourself at home. Okay, if you have a wire connected to your laptop, and you turn it on, and you have a little compass that's sensitive enough, if you put it on the left-hand side of the wire and the right-hand side of the wire, it should, if you put it the left, the top, the right, and the bottom around that wire, you'll find that the needle is deflected in different places. Okay, so let's try this ourselves. So when we do this, it turns out that the current carrying wire, if the wire is going horizontally, this is not, this is just a wire, okay, then the magnetic field is at 90 degrees, okay, it's at 90 degrees to that, so it's at 90 degrees, and oh, that's a bit too thick, I think, that pen. Here we go. It's at 90 degrees, okay, and it's circular. In this case, we're looking at it kind of into and out of the page, okay. So that's what it is, okay. So that's a bit of a funny drawing, but let me draw that again. I don't know if there's a wire going this way, okay. Then the field will be circular around it, okay. It's going circular, okay. Alrighty. The next question is, okay, well, which way, would the field be going if the current's going this way? How do I know? Okay, so for a current carrying wire, we use the right hand, and most of our rules are right hand rules. You use your right hand for most rules, apart from generators. Okay, apart from generators, in electromagnetism, you always use your right hand for any of these. We've got a few sign conventions. We've got this one here, which will show a force on a force, a magnetic field, and a current. And this one is called the right hand grip rule. Okay, so what we do is, when I'm looking at this, my current is flowing this way, okay? And so the way my fingers curl will show me the magnetic field around that current, okay? And this works in opposite as well, okay? So if this is a magnetic field, then this will show me the way my current is moving. So this is called the right hand grip rule, okay? So you must use your right hand for this. Okie dokie. So let's try and use this. So let's say indeed that my current is going this way. Okay, so my current is flowing this way. We know, and I'm just going to signify this for your sake, in sort of small dashed green lines, that in actual fact the electrons are flowing the opposite way. But we always take our conventional current, okay? We always take conventional current, conventional magnetic field, okay? So this is from positive to negative. So we know that the positive side must be somewhere here and the negative side must be somewhere there. In actual fact, we know the electrons are moving the opposite way, but we take it conventionally, okay? All right, so if we do this, I'm going to draw in red. Let's use our right-hand grip rule to say which way would the magnetic field around a single current carrying wire look like. Okay, so I'm looking at this and it's going, I'm kind of looking, I've drawn it into the page, so it's kind of going this way, right? And so it looks like it's going clockwise, okay? So if I'm looking at that, the thumb points in the direction of the current, and the way your fingers curl is the direction of the magnetic field. Okay, so if I do it the way up, yeah. Anyway, okay. So that's that. So you can see that my thumb is going to be pointing there. My fingers on my right hand are curling this way. If it's pointing in, they're curling this way. So it's a clockwise field, and that's how the magnetic field would look like. Okay, so if you do have a current carrying wire, and as you know, the field would get weaker and weaker as you go further away from that current carrying wire. Okay, it would be weaker and weaker. Okay, and if you turn off the current, there is no field around that current carrying wire. Okay, now it's important to note that this thumb is conventional current. Okay, so we actually know in actual fact that really the electrons are flowing the other way. All right, so they can sometimes give you a charged particle like an electron and say, oh, what would be happening? And so what you have to do is, in your head, you have to think about how that would work out. We'll do that in later videos. I think I might just leave that video there, and we'll address these next 2 points of what happens if you coil a wire and the rest of this stuff on the next video. Thanks, guys. So today we learned how to use the right hand grip rule. if you have a conventional current flowing through a wire, how do you know the magnetic field that is around it? Okay, so if we scattered some, I don't know, if we scattered something around, if we scattered some magnetic particles around a current carrying wire that was going into the page, they would align themselves in this kind of pattern. Okay, thanks, guys.